Welcome to Lab 2, which presents a revision of the results that we found from Lab 1. The purpose of this lab is to compare the electric force calculation between the point charge model that we used last week and the line of charges model that we used this week. Since we made the assumption to model the tape as a point charge, we want to see if we can get a more accurate calculation by modeling the tape as multiple consecutively placed point charges or a rod. From this lab's results, we found that the estimated charge of the tape using a line of charges model was 3.52 times 10 to the negative 8 coulombs, while the estimated charge of the tape when modeling the tape as a point charge was 1.43 times 10 to the negative 9 coulombs. The line of charges model gave us an estimate that was 10 times less than our estimate when we used the point charge as our model for the tape. Here are some important principles that we use for this lab. First, we use the electric field equation to calculate the electric field produced by each point charge in the rod. This calculation will then be used to calculate the force on the top tape due to the electric field produced by the bottom tape. We use the Coulomb's law to calculate the excess electric charge on the floating tape using the force calculated from the electric field calculation. Third, we used the gravitational force equation to calculate the force due to gravity on the floating piece of tape. Since we're comparing the results from Lab 1, here's a quick overview of what we found last week. We found that the estimated calculated charge of the tape is 1.43 times 10 to the negative 9 coulombs, and we found that the distance between the top tape and the bottom tape was around 0.025 meters or 2.5 millimeters. And here we see to the right the computational model that we got from Lab 1, where the blue represents the system, the top tape, and the red represents the source, which is the bottom tape. Here are the calculations that we made during Lab 2. We calculate the gravitational force just like we did last week by multiplying the mass of the tape, which is 3 times 10 to the negative 4 kilograms, with the acceleration due to gravity, which is 9.81, giving us a downward force of 2.94 times 10 to the negative 3 newtons. Since the tape is stationary, we can conclude that the electric force should be equal in magnitude and opposite in direction. So the electric force due to the bottom tape is also 2.94 times 10 to the negative 3 newtons in the upward direction. Finally, we can calculate the charge of the top tape using the equation for calculating the force exerted by the bottom tape on the top tape. Here we use the E field of a rod since we are modeling the tapes as a line of charges, which is a characteristic of a charged rod. From rearranging the equation, we can solve for Q, which is 3.52 times 10 to the negative 8 coulombs. Here's the computational model used in Lab 2. On the left, we see two functions. The E field function is used to calculate the E field caused by the charged particle at the observation location. The line charge function initializes a line of point charges arranged at equal intervals to simulate a rod with a uniformly distributed charge. To the right, we have a nested for loop that uses the E field function to calculate the net E field using the principle of superposition by adding the E field from each point charge of the rod. Here are the results of the computational model. The green arrows represent the E field from each point charge, while the yellow arrows represent the force due to gravity. Here are the assumptions and errors that we made during this lab. First, the assumptions. We had assumed that the tape had a uniformly distributed charge, even though there was no way to prove that the charge had been distributed evenly after charging the tape. We had also assumed that air resistance was a negligible force, especially in this model. Another error we made was that the measurements during the data collection during Lab 1 could have been imprecise, especially when measuring how much the top tape had moved in the presence of the bottom tape. Lastly, we handled the tape too much, leading to neutralization of the tape, which could have skewed our results. Here are the discussion questions for this lab. What if we had modeled each of our tapes as a single point charge, like in the previous lab? In the previous lab, we found the estimated value of the charge of the tape, when represented as a point charge, to be 1.43 times 10 to the negative 9 coulombs, while the line charge representation of the tape gave us an estimated value of 3.52 times 10 to the negative 8 coulombs. These estimates likely differed because a point charge is a very generalized estimation / representation of this tape. The line charge is likely closer to the value because the tape is better represented as a rod than a point charge. The charge at the tape is distributed across the horizontal length of the tape rather than at a concentrated point like we did in the point charge model. In conclusion, the representation of the tapes as two rods is likely a better estimate of this model. The results of this lab show that it requires less charge to balance the tapes against gravity when compared to our results of the point charge representation from lab number 1.